Hello, it's Keith here, and this is lesson 2 of the multi-platform series of my 6809 assembly programming tutorials. If you saw one where we were looking at random numbers and also range checking, you know I was making a little game which I was calling Suck Shoot. I made in the past a game called Suck Hunt on the Amstrad CPC and a few other Z80 systems, but that was a very complex game and wasn't really possible to port to other systems. But for the other systems that I can't put Suck Hunt to, you can play Suck Shoot. So this is a miniature game which is very simple. We've got bats flying towards the screen and we can shoot the bats with our crosshair. Now, last time we were range checking to see if the crosshair was pointing at the bats, but there was nothing really happening when we did. Now we've got a score. You can see it at the top of the screen here. Now, this is what we're going to be looking at today. This is in something known as binary coded decimal. Hexadecimal is, of course, very good for calculations, but it's a little bit tricky for us actually getting numbers onto a screen. So a binary coded decimal is much simpler for getting onto the screen, but a little bit more tricky for calculating. We're going to be looking at how to use it today on the 6809. So you can see we've got our score, which goes up quite nicely. When the bats get to the front of the screen, we will lose a life. You can see the counter in this corner went down by 1. It's now down to 3. When it gets to 0, we'll get a game over, and then it will calculate to see if our current score is higher than our high score, which it will be because it's currently 0, that high score. So if we just wait a moment, we'll see that. And that's another thing we're going to be looking at. We're comparing two binary coded decimal values. So today, there we go, got a new high score, good for us. And you can see the title screen now shows the new high score. We're not going to be actually looking at the Suck Shoot game today though, because we're going to do a Vectrex example on that, covering the code, because it's all Vectrex code. We're just going to be covering the code that is behind it. And for that, we're actually going to be using the Dragon. So we're going to be using the Dragon instead because its screen's a little bit more consistent. So that's what we're going to be doing. So what is binary coded decimal? Well, let's go over to the blackboard and we will discuss that. So, binary coded decimal. Well, of course, when we're working in hexadecimal, we'll have numbers in a byte that will go from 0 to 255, which is FF, which is very good for our mathematics, but as I say, will cause us some trouble. Now, when we want to show stuff onto the screen, we're going to use something called binary coded decimal, and this is very simple, really. It takes each of these digits in our hexadecimal, which of course is made up of a nibble, 4 bits, and instead of going from 00 to FF, it goes from 00 to 99. Now, the byte, of course, would then continue to go to A, B, C, D, E, and F, but we're going to skip those, quite literally skipping over those values. So if we've got a value of 09 and we add 1 in hexadecimal, we would end up with a value of OA. But binary coded decimal will correct that. It's literally a correction function, and it will convert OA to 10. We have a command to do this correction. It's literally a correction called DAA, Decimal Adjust Addition. It stands for on the 6809, I believe. It stands for something different on the Z80. It stands for Decimal Adjust Accumulator on the Z80 because it works slightly differently. So that's basically what we're doing. We're going to be doing our addition, and then we're going to be correcting the byte values, and we're going to use a carry because we're going to be using multiple byte values. We've got 8 digits. I like to have a nice pinball style score with lots of zeros. It looks nice, it makes your game feel exciting. So I'm going to be using 8 digits, and that is 4 bytes. You can see 1, 2, 3, 4 bytes. And of course, if one of our values is already at the limit of its binary coded decimal byte, for example, if this is 99 and we add 1, well, we're going to have to carry over into this, and this would become 01. And this would become 00. So we're going to be doing a carry operation as well. So that's the theory of what we're going to be doing. Let's go over to our source code and let's take a look. So what we're going to be doing today is we're going to be doing a couple of mathematical operations. We're going to be doing an addition. We're going to be doing an effective subtraction. Now on the 6809, the DAA command only works with addition, so we'll actually add what I believe is known as a tens complement value, which is effectively subtracting 1 by an addition command. Bit weird, but that's what we'll be doing. We'll be doing a comparison, and we'll be showing the results to the screen. So we're creating 3 commands: addition, show, and compare, and we'll be looking at those today. Now, the format that I'm using for my values is a little endian value. So we've got 4 bytes here, which is our 8 digits of binary coded decimal data, and this is a value of just 5, because this 5 here is the least significant byte in this 4 byte 8 digit binary coded decimal sequence here. So that's how we're working. The other thing is the addition commands require both of the parameters to be the same length. So our destination parameter here is 4 bytes. So our addition parameter needs to also be 4 bytes the way I've coded it. So that's what we're going to be doing. So the first command we're going to try here is going to be, the first command is going to be a show command. So we're showing the binary coded decimal string at memory address 3000, and we are going to be showing 4 bytes. And the way my functions work, b is the length in bytes, and x and potentially y, depending on the command, are going to be pointers to the binary coded decimal data. Now hexadecimal 3000 is in memory because we're going to need to change it. My program is currently running from ROM, you see, so I couldn't directly use the test value, which is this one here. I couldn't use the address BCD1 because it would be read-only, so that's why we're doing that. Now let's have a look at the results, and then we'll look at why those results were the case. Okay, so here's our program starting up here, and you can see here we've got 1, 2, 3, 4, 5, 6, 7, 8 here, and then we've done an addition here, and we've effectively added 5, and so we've ended up with 1, 2, 3, 4, 5, 6, 8, 3. Well, if we get our calculator up here and we do 1, 2, 3, 4, 5, 6, 7, 8 plus 5, well, we end up with 1, 2, 3, 4, 5, 6, 8, 3. So that has indeed worked as we would expect. Pretty logical there, but we just need to confirm these things, make sure everything's working right. So our mathematics is indeed working. And of course, we have used our show command to show these values to the screen. So when we're doing a show command, we're specifying the length and the BCD variable to show in X. When we're doing an addition, we of course need 2 parameters. The X is the amount to add and the Y is the destination. And we're going to have a look at the commands we're using to do that right now. Okay, so how do we show the strings to the screen? Let's look at that first. Well, the first thing we're needing to do when we're showing a string to the screen is we're showing the most significant part first. The least significant part is 7, 8 there. The most significant part is 1, 2. But because we're reading left to right, we need to show the 1, 2 first. Now, the length of our string is 4 bytes. So we're using this lex command to effectively add b to x here. So that effectively does x equals x plus b, adding 4. And that will put us 1 byte after the end of the string. But our first command is load a from x with a predecrement. So x effectively does a -1 and then reads in from the memory address in x. And so we're going to get that first most significant byte there. We're then taking that read in byte and we're using the print BCD char, which will show that byte to the screen. The way we do this is we take the most significant nibble and we switch it to the bottom using this swap nibble function I've got here, and then we use print BCD char 1, which will show a single digit, and we use that twice, first for the high nibble and then for the low nibble here. And all it does is it effectively adds 0 and then it runs the print char routine, and that will show an ASCII character to the screen. So this is showing a single byte, 2 characters, and what we're doing here is we're using this b times, repeating each time, showing those characters to the screen and then returning. So this function is showing our binary coded decimal value to the screen. Our add function is doing our addition, and of course, as I say, we can use it for subtraction if we have a negative value in tens complement. And what we're doing first is we're clearing the carry, because we're going to be working with sequential bytes from the least significant to the most significant, adding any carry as we go along. We're having to clear the carry first, so we're doing an AND CC here, and we're effectively clearing the carry there. Then what we're doing here is we're loading in the value in the destination, and we're adding with the carry the value in the parameter to add in x here, and we're incrementing the x pointer as we do. We're then using the decimal adjust for addition command here, which is correcting the values and dealing with any wrap over if we've gone over the 9 value into A to F and wrapping that into the next digit. So that's correcting that. And then we're storing it back to the Y destination, and we're incrementing the Y destination there. We're then just repeating for the remaining digits, and because we are using add with carry, that will pass any carry along from the least significant bytes along to the other ones. So that's how we're doing our addition, and you can see that happening just here. So what about subtraction? Well, subtraction is a little bit of a pain. basically we need to use something known as tens complement, and what this is effectively we take a value where all of our digits are nines, we subtract the value we would actually like to work with. For example, if we wanted to work with -3, we would fill all of our digits with nines, subtract 3, and then we add 1, and this is very similar to our mathematical calculation for working out a negative value in hexadecimal. So we're effectively subtracting our value +1. So for example, if we wanted the value -1, we would take all our nines there, subtract 1, which would give us nines and an 8. We would then add 1, which would give us all nines. If we wanted a -2, then that would effectively be all nines and an 8. And we can try that out in our code. We will be doing that. So we've got some test values down here. We've got a minus here, which is a -1. And then we've got a second option, which is a -2. You can see here. So all nines, 9, 8 is -2. All nines is -1, and so on for higher values. And all we need to do to effect a subtraction is we use our BCD add value with that tens complement minus value. And that's exactly what we've done in our test here. We've taken our 1, 2, 3, 4, 5, 6, 8, 3. We've added that tens complement of -2, and it's gone down to 8, 1 here. So that's what we've done. Now, if we just change this code here, and we change this to the -1 version, and we run again, well, you can see now it's gone down by 1. So we can do subtraction. We just have to have a bit of a pain working out that tens complement there. Now, what about comparisons? Because our game is going to need to do some comparisons to work out which of the scores is higher, the current score or the high score. Well, we're going to do that, and we're going to create a command which will effectively return the same flag settings as our usual compare command, only comparing an entire sequence of binary coded decimal values here. Now, if I just run the example here, what we're basically going to do here is we're going to compare BCD1 with BCDCP here, and you can see in this case the carry flag has been set, and this is going to effectively set the flags the same as subtracting the value in Y from the value in X would. Now in this case the value in Y is higher than the other value, so the carry flag is going to be set, and so we've printed a C to the screen. But if we change our test value here, if we just disable this one, if my mouse stops moving, and we enable this one, which is a lower value, and we run again, well, this time the value is lower because that bottom byte has been changed to a 0, and so this time no carry has occurred. Of course, the other possible scenario would be the two values are exactly the same, and in that case we want to get a 0 value. Now my game doesn't require that, but it would be something you would want to see, and the test function has returned a 0. So how do we do this comparison? Well, it's pretty straightforward. We don't actually need anything particularly special to compare our binary coded decimal values. We don't need any kind of decimal adjusting because we're only doing comparisons. All we do need to do is we need to start from the most significant byte, because obviously if the low byte is higher but the top byte is lower, it's that top byte that's going to decide which of the two strings is the higher or the lower. So we're moving to the end of the X and Y parameters here by adding B to them. We're then reading in with a predecrement here from the X parameter, and we're comparing with predecrement to the Y parameter. And if these two are different, then because we're comparing the most significant first, that is going to be the decider on which of these two parameters is higher or lower. So we're immediately going to jump to the end here, and we're going to return. But if those two parameters are the same, then we need to move to the next most significant byte in the sequence. So what we're going to do is we're going to decrease our counter here, and assuming we've not got to 0 yet, we're going to repeat and we're going to compare again. And we're going to keep comparing until we get to the end of the sequence, or we find a difference. Now if we get to the end of the sequence, we're going to return anyway, and the 0 flag will be set to denote that the two are the same. So there we go. So that's how we can do our comparison, and that's exactly what is being done in the suck shoot game. Exactly what you just saw. We've got 5 points here that we add whenever the player shoots an enemy, and we've got a game over sequence here which compares the score and the high score, and if the carry is set and the new score is lower, then we're going to show a message telling the player that they've not done very well, and if they've got a high score, we're copying the current score to the high score with this load and increments function I've written here. So there we go. So anyway, that's all we're going to be covering this time. You can go to my website and you can download the example code for today, and you can download that little game if you want to play it. We'll be looking at the code that makes up the suck shoot game next time. We're going to go over that on the Vectrex. If you've liked what you've seen and you want to support my content, you can become a patron. As you can see, the patron list there. You can also buy my book, which doesn't cover 6809, but if you're interested in the other systems, it covers Z80, 6502, 68886 and ARM. It's available on Amazon. Anyway, I hope you've enjoyed this. Go to the website, get the code, and have some fun with it. Hopefully you can make some little games of your own with it. Hope you've enjoyed this. Thanks for watching today, and goodbye.